application of equilibrium to what? To Haber process. That is the manufacture of what? The manufacture of ammonia in what? In industry. The manufacture of ammonia in industry. So I want to see if you could recall anything about the manufacture of ammonia. What would be your raw material?
So it's nitrogen and hydrogen.
Okay, so you have the manufacture of ammonia. So in industry, ammonia is manufactured from nitrogen, okay, and what? And your hydrogen, right? That gives you, that should be 2NH3. So that's a gaseous what system. Another thing to establish is that the forward reaction is what? The forward reaction is what? Is exothermic. Okay, yeah. So most of the reaction, most of the ammonia used for the manufacture of fertilizer, okay, are obtained this way. They're obtained this way. So how do you obtain your nitrogen? Okay, so you need to know that your nitrogen is obtained from where? The nitrogen is obtained from where?
Is it from fractional distillation?
Yes. Oh my God. Thank you so much. You are really on top of your game. Brilliant. So they are obtained from what? From air. That is fractional distillation of liquid air. Fractional distillation. Though I'll tell mommy to order special pizza for you. Okay. Yes. Fractional distillation of liquid air. Okay, that is how you get that. So what about the hydrogen? Where do you get the hydrogen from? Because it's very important you know this background. The hydrogen is obtained from, where? It's obtained from where? You want okay, let me help you. Methane. It's obtained from methane. Methane is your natural what? Natural gas. Yeah. So it's obtained from methane. You can crack your methane. Okay, break it down. So obtained from methane, or it is obtained by reacting your methane plus plus steam is going to give you this. That is getting hydrogen from what? From that. Okay, it's going to give you this, and of course your carbon monoxide can further react with the steam, okay, which of course is water, to give you this. So this is how to obtain your what? Hydrogen for the manufacture of what? Of ammonia. So you can see that equation. Please, you need to know this equation. Your steam plus your methane will give you carbon monoxide and what? And hydrogen. Of course, carbon monoxide will remove oxygen from what? Hydrogen, to give you what? I mean, oxygen from water to give you what? To give you hydrogen, carbon dioxide. Okay. So having established this, let's now see how we arrive at a state of compromise in the manufacture of what? Of ammonia. Let's see how we arrive at a state of compromise in the manufacture of what? Of ammonia. Okay. So what do you call it? What is the catalyst used in the manufacture of ammonia? Let's see if you can record that.
That is an iron catalyst.
Okay, yes, you use iron catalyst. The catalyst is a what? We say it's a finely divided what? Divided iron. And of course, you know what implication of finely divided. Why do we need to make it a powdery what? A powdery form? Why do we need to make it a powdery form?
So to increase the rate of reaction.
Thank you, to increase the rate of reaction. So that is number one condition. So number two condition is that this reaction takes place at what? 200 atmosphere pressure. Okay, 200 atmosphere pressure. Okay, and of course the optimum temperature Okay, it's about 450. Optimum temperature, sorry, is about what, 450 degree what Celsius. So the question now is, just like we looked at for Haber process, want to see how did they, arrive at this particular what condition. How did they arrive at a condition like this? That's what we want to focus on. So don't forget that we'll look at those conditions. We'll talk in terms of rates, right? In terms of rates, we'll talk in terms of yield of reaction, and of course in terms of cost. Very important. Okay, so let's say if we increase temperature for this reaction, what will be the effect on rate if we increase the temperature? What will be the effect on rate?
So the rate of reaction will increase.
The rate will increase. Okay. What about the yield?
Says the reaction is
The forward
exothermic.
reaction is exothermic. Forward reaction is exothermic. Delta. Yes, forward reaction is exothermic. So what will be the effect?
So increasing temperature will reduce the yield.
Will reduce the what? The yield. Yes.
Yeah.
Yes, the yield will be what? Reduced. The yield will be reduced. Okay. So what about the yeah, so we have looked at that. Okay, reduce the yield. So really, I know that in industry, I can't be increasing my temperature too much because the yield is going to what? The yield is going to decrease, right? So then what about pressure? If I increase pressure, if I
So
increase the pressure,
the rate of reaction will increase.
the rate of reaction will increase, yes.
And the yield will increase actually.
The yield will increase, right? The yield will
Yes.
increase. Okay, the yield will increase. Okay, so what about the cost?
So the increasing the temperature and increasing the pressure are both very expensive, or they increase cost.
Yeah, so there will be an increase in engineering costs, right? The cost will increase because we want more pressure. I mean, higher pressure increases the rate, yes. Okay, but higher pressure requires what? Requires bigger pipes, a lot of engineering work that needs to be done. It will increase what? It will increase cost, right? And it's also going to what? Increase my yield, but I can't increase the pressure what too much. Now, let's see how we can just relate that. Let's assume that in industry. So how would they come to a state of compromise in industry? So let's assume that I have my pressure here. Okay, let's assume that I have my pressure here. It's as a a pressure is at 100. I have 200 here. I have 300. Okay, I have 400. 400 here. Okay, so let's say this is my yield. My yield in industry. My yield. I have, let's say 10%, 20%, 30%, 40%, 50%, like that, 60%. So if I, if I look at the rate of reaction is usually, so let's assume I have something like this. Okay, if this was done at 350 degrees Celsius temperature, then I have another one that is done at 450 degrees Celsius temperature. Then I have another one that is done like this. Let's say this is 550 degrees Celsius. So maybe when I plot a graph of, in industry, I plot a graph of yield, my yield of ammonia against pressure at particular temperature. This is what I got. Okay, this is what I got. Okay, so, and I'm not looking at, okay, which pressure am I going to choose? Which pressure am I going to choose? So if I say, let's say 200 here, if I choose 200 at 550 degrees Celsius, which is a higher temperature, okay, I'm going to be getting what? My yield will be what? 20%, right? My yield will be 20%. This will give me 20%. Okay, 20%. But if I still maintain 200 at 450, my yield will be around 40%. Okay, 40%. But if I maintain that at 350, okay, 350, what do you call it? I'm looking at another yield, but the temperature is lower. That means that my reaction will be what? Will be a bit slower for me. That means I want to get my ammonia quicker at a reasonable rate, and I want it at a pressure that will not cost me much. So in industry, they arrive at what? They arrive at a state of compromise, 200 atmosphere, 450, okay, degrees Celsius as their water temperature, and of course the use of what? The use of catalyst. Okay, so it's very important to note that. Okay, so why do we use the optimum temperature of 4 degrees Celsius? So 4 degrees Celsius, okay, is low enough a temperature to what? To get a reasonable what? To get a reasonable yield. To get a reasonable yield, but high what? But high enough, okay, to have what? High enough to have a rate of reaction, that's what produces ammonia, fast, okay, enough to be what? Economical. To be economical. That's a good summary to that. Okay, 450 degrees Celsius is a reasonable temperature that is high enough for me to have a reasonable rate, and low enough for me to have what? Fast enough for me to have a reasonable rate of reaction, which is economical, and it's low enough for me to have a good what? A good yield. Okay, so if you put everything together, you have a better understanding of how equilibrium is applied to what? To industry. So looking at a Haber process here now, 200 atmosphere, okay, a pressure, increase in pressure, increases rate, and increases yield. Okay, so the only thing is that it will increase what? It will increase cost of production. So we have to we can't increase the pressure too much. So maybe 200 atmosphere is okay. It's reasonable enough to give us a reasonable rate, a reasonable yield of ammonia, and at a reasonable cost. 450 degrees Celsius is low enough. We could have gone higher, but it's low enough to get a reasonable yield of ammonia, okay, at a reasonable rate of what? Of production. Okay, so this is the application of equilibrium to what? To chemical industry. Okay, any question? Any question?